למשל, שאתה יכול לאמץ ככה. כי לא כל כך קשה.
כאילו, את יכולה להחליט שאת מסתכלת לתוך העניין את ההסכמות שלך, אומרת, טוב, נעשה משהו, ניתן לאינפוט, נסתכל על זה, נראה איך עושים זה בעצם מה שיגיע, זה ממש כאילו תלוי אבל יכול להיות באמת בפסיכולוגיה, יכול להיות שזה ספציפים אחרת, אבל כאילו, זה בערך הזה.
הקוגניציה זה לא גישה שנותנת לך תחזיות. זה לא כזה שיש לך תחזיות.
לא, היא אומרת, אנחנו רוצים להסתכל על אנחנו רוצים לחקור את מה שקורה בתוך החשיבה. אנחנו מניחים שיש דברים שיש שם דברים של...
גישה רווחת קוגניטיבית.
מה?
גישה רווחת קוגניטיבית, זה לא... קוגניציה זה מדע, קוגניציה זה כמו ביולוגיה. ביולוגיה זה לא גישה, זה תחום.
לא.
זה תחום אחר, אתה יכול לחקור אותו בכל מיני שיטות.
לא, בסדר. קוגניציה לא כמו שם לחקור את קוגניציה. כלומר...
זה תחום אחר.
כלומר, זה עולם מילולי זה כאילו נשמע ככה, אבל זה לא משמעות של זה. כלומר...
זה קוגניציה, זה תחום אחר.
לא, אבל אתה עושה דברים מסוימים, אתה...
נכון, אבל זה תחום אחר.
אני לא מבין מה המשמעות של דבר שתחום מחקר, נגיד, בניגוד זה ובניגוד זה.
ביולוגיה זה לא תחום מחקר, זה גישה שאומרת לך קוגניציה זה תחום מחקר.
אני לא מבין למה...
אתה בוחר לחקור קוגניציה.
זה לא משמעות, זה לא שתחום המילים, הקוגניציה.
זה תחום של מילים.
מה? זה לא כאילו המדעים של קוגניציה, כלומר זה לא תחום של הקוגניציה. זה לא זו הייתה הגדרה מילולית שקראו לזה ככה. אפילו שאני זה, כאילו...
מאיפה ההגדרות המילוליות האלה שצריך לקחת?
בגלל זה אני חומסקי. כאילו, כשנקבע מונח לראשונה, הוא היה... לא, זה היה מישהו אחר שהיה איתו אגב בצד המחר אפשר לבדוק את זה. לא זוכר את השם של מישהו אחר. אני יודע בדיוק באיזה דרך אני קורא, אבל כאילו המונח נצבע בזמן, ברגע ספציפי, כאילו, זמן לפני. מדעי הקוגניציה, אתה זוכר מי טבע את זה, את השם הזה? כאילו מי התקרב בראשונה?
למה שידע את זה?
זה...
שהוא מהחבר'ה החומסקיאנים כזה?
אני זוכר שחומסקי היה שם באירוע, אני לא זוכר כאילו מה... אני לא חושב שזה היה הוא כאילו ש...
פודו? לא יודע.
פודו? נראה לי לא...
לא, אין לי...
כאילו הוא אדם שאתה יכול לעבור ואומר כן.
סתם הוא הבא בתור, כאילו.
אבל...
באמת זה הבא בתור?
בתחומים האלה?
כנראה שכן.
נראה לי שכן. מה, מודולריטי אוף מיינד? כל הדברים.
זה לא...
הוא מהאנשים מאוד מפורסמים ללא ספק, הוא ודאי בטופ...
אתה יודע, רגע,
זה מישהו, אני חושב שזה מישהו שהוא היה כאילו קצת...
מר או
דיוויד מר? לא... הוא לא מהפכן, אבל הוא לא כאילו... מדעי הקוגניציה לא יכולה בעלות באותה רמה כמו...
אולי, לא יודע.
אני חושב שזה היה... רגע שמישהו הציע את זה, ואני כאילו לא תפס, אבל לא...
לא יודע.
מי
tell you that there will be no extra PA hour today. She cannot make it. There will be the regular one. And I probably, because of the early hour, the change of time, forgot to bring my tablet, so I need a moment to print my notes. Almost there. Almost there.
Are you going to print them?
I'll print them, yes.
Ah.
Mais cette fois-ci, les
Et
algorithmes
voilà,
statistiques au niveau d'une cellule,
הם כאילו, הם גרים אלה מרחוב התיכון?
כן.
סליחה.
לא,
שנים שלי.
עוד לא, כי איך הוא vraiment de cette place,
הוא עבר.
הוא עבר avec des terrasses,
אוקיי, איפה?
אבל באותו רחוב.
באותו רחוב. הם עדיין שכנים שלי, של ההורים שלי.
Anyone taking notes? No? Okay, so we continue our discussion of encoding of multiple variables. We just need to wrap up the results that we got. So let me remind you. We discussed the PC solution, which has the form W transpose PC is a projection on the first M principal components, and then once one projects on them, each one of the coefficients is encoded separately, but with some amplitude, and so the amplitude are in this matrix. And the general solution is a unitary transformation, any unitary transformation times W transpose PC. I don't remember if I put here U or U transpose, so it's just a matter of decision. Do you remember? Let's see. Yeah, like this. Okay, so now the question is, what are the alphas? And we got, by optimizing the Lagrangian, by optimizing the Lagrangian, we got equations for the alphas. And so they have the following form: alpha I written as a function of the Lagrange multiplier, and as a function of lambda I, epsilon, and delta, the noise, had a certain expression. I'll write it down: delta divided by 2 epsilon, but you have it from the last lecture, plus lambda I, and then plus square root of 2 epsilon plus lambda I squared plus 4 epsilon of lambda I over delta minus lambda I. Here I'm not sure, it's cut off in my printout. Anyone knows what should be there? I'll see in a moment.
minus epsilon.
Minus epsilon? Okay. Okay.
If my transcript from
Yeah.
last lesson is correct.
Okay. Well, now I can check. It's taking Microsoft some time to load anything. Almost there.
Yeah. Okay. So I want to make and the Lagrange multiplier needs to be chosen to set the constraint. We'll write that down in a moment. But I want to first make some comments about this equation. First of all, remember that we had the quadratic equation. And so this is the positive solution. And that's a relevant one.
Why would you choose the positive?
Well, as normally we have to discuss something about this. The other one will be negative, so the square root of alpha I needs to be positive. Okay, the positive solution of the I mean, this is the one with the plus, and this one is positive of the quadratic equation. Now, let's think about how alpha I depends on the Lagrange multiplier. So remember, tuning, we know that for tuning the Lagrange multiplier is equivalent to tuning the variance, the total variance that we allow in the output units, right? And we first need to see in which direction it goes. So when we increase large lambda, the Lagrange multiplier, I think there's a yeah, this becomes smaller, right? This becomes smaller. So alpha I becomes smaller. So larger lambda, smaller alpha I. And in particular, when lambda goes to 0, then what happens? Then this diverges. So alpha I diverges. Alpha I goes to infinity. So the limit of large lambda going to 0 is the limit where the output variance is allowed to be infinite, extremely large. And if we want to reduce the output variance, we need to increase lambda. But one thing to note is that at some point for each one of these expressions, for each one of the alpha i's, at some point, this becomes negative. Right? So what is written here, so let's imagine that large lambda is 0, then this is infinite. Okay? Now we start to reduce it. At some point, this will become negative. When this will become negative, the square root will be smaller than 2 epsilon plus lambda, and so this whole expression will become negative, which doesn't make sense. Okay, so there is a maximal value of the Lagrange multiplier for which neither one of the two solutions of the quadratic equation makes sense. Both of them are negative. This is square root of alpha. So let me write that down first, and then we'll discuss what that means. So this solution, the solution that I wrote here, is relevant only if the Lagrange multiplier is smaller than lambda I divided by delta lambda I plus epsilon. That's the value for which this thing becomes negative. And this depends on the lambda I. So for each one of the m projections that we're encoding, this will happen at a different value of the Lagrange multiplier. Let me denote this by large lambda I star. So something here is weird because we got a solution for alpha I. We tried to get a solution for alpha I. Alpha I is supposed to be the square root. I mean, this is alpha I or a square root of alpha? I know this is alpha I. But we got a solution for alpha I, and alpha I has to be positive. And we don't get a positive solution for alpha I. So one thing to note is that there is actually another solution for alpha I when we take the derivative of the Lagrangian with respect to alpha I. And the reason is that the Lagrangian is actually, we're optimizing with respect, the Lagrangian is written in terms of square root of alpha I. And actually, we can think about the expressions that I wrote as expressions that we're optimizing with respect to the square root of alpha I. Alpha I is the square of the square root of alpha I. And if alpha I is 0, and the square root of alpha I is 0, the derivative with respect to that is 0 as well. So what happens if you need to look back at the Lagrangian and convince yourself that for every I, alpha I equals to 0 is also a solution. Or a solution of the equation dl to d alpha I, or it's dl to the d square root of alpha I equals 0. So in fact, for every one of the alphas, there are three possible solutions of this differential equation. Two of them are the solutions of the quadratic equation that are written here. One of them we always can rule out because it's negative. Another one is sometimes positive and sometimes negative, and then there's also this one. And so we have to decide which one is the correct one to choose that actually does give us the maximum of the Lagrangian. And I will just tell you the answer. The answer is that as long as we're in this condition and this solution is positive, we should choose this one. And once lambda becomes, for every one of the projections, once lambda crosses this threshold, at that point you can see that alpha I exactly becomes 0. That's the point where this solution crosses 0. And from there on we take this solution. So this tells us something interesting. Okay, it tells us, so remember, increasing the Lagrange multiplier is decreasing the allowed variance of the outputs. Okay? And what this is telling us is that if the variance is sufficiently small, we simply stop encoding some of the projections. Which ones? This happens faster. I mean, this thing is a monotonically increasing function of lambda. So the larger lambda, the higher the threshold. So we first stop the ones encoding the ones with the lower variance. Okay? So in fact, if we have, these m variants, the m projections, each one with its own variance, as we allow less and less variance at the output, we stop encoding some of them, going from the ones with a smaller variance up to some point where we might encode only one. Yeah.
Maybe start to understand. You said that there are three possible solutions.
Yes.
And
That was a long time ago, so I'll have to repeat many sentences.
No, I just took, and two of them came from the quadratic
Yes.
equation, but you said that one of them
One of
ignored
the one where we had a minus here,
Okay.
that one is always negative, so we know that it's irrelevant.
Okay, so we have two
So we have two,
that we consider.
right, there are two that we
One is
consider.
0 and the second
One is sometimes positive and sometimes negative, it's this one, depending on large lambda. So if it's positive, we choose this one.
Okay.
And if it's negative, and when lambda crosses this value, this becomes 0, and from that point onward, we choose this one.
And what did you say about the interpretation?
Okay, so I said that if the allowed output variance is sufficiently small, we stop encoding some of the coefficients. We set their alphas to 0, and we devote all our resources only to a smaller subset of the projections. So So this depends. For the equation of the Lagrangian actually has an extremum. It has the equation dl to the alpha square root of alpha I equals 0 is obeyed for alpha equals I equals 0 for any I. It's simply because of the fact that the derivative of L with respect to this is square root, is like you take if you would call this x, And so the derivative of L with respect to x is L is written as a function of alpha I, so it involves x squared. Okay, that I think maybe I said it incorrectly before. When you look at the expression for L in your notebook, it involves alpha I. Okay, but the real parameter is square root of alpha I. That's what exists in this matrix. So we need to actually think about it as if we're taking the derivative with respect to this. But the derivative with respect to this, because the Lagrangian involves this squared, it like involves 2 times this times the derivative with respect to this. So when square root of alpha I is 0, that's always a solution to this equation.
But if all alpha i's are 0, then we start encoding all of them.
That's right. So in general, for each one of the alphas, we have to decide which one of these we're taking. And I'm telling you the correct choice to take is to encode, always use this solution if it's possible, if this is positive. Now it's true that if we increase the lambda beyond this value, beyond this value for all the i's, then something even stranger is going on, and this solution tells us that we don't encode any one of the coefficients, which doesn't make sense, and I leave it for you to think how to interpret that. It's not a big deal, because actually the relevant range of lambda is actually up to the one where there's still one unit that we're encoding. Yes.
So lambda is a Lagrange multiplier, and what does it mean I mean, like you said, it means the maximal variance.
Well, the Lagrange multiplier is something that we need to tune in order to set we have the parameter Q, which was the variance of the output units. So there's a one-to-one mapping between the Lagrange multiplier and that parameter, and you see that it's monotonically decreasing. As we increase lambda, the variance at the output decreases. All right. So maybe I'll write it down to decrease Q, increase large lambda. Q is the variance per unit output unit channel. Large Q is that minus the variance of the noise. But anyways.
But Q depends on the small q, which we decided.
Yeah. So Q is equivalent to Q. I could have written here Q.
But we decided the small q.
Yes.
We gave it as a function.
So right. So the rules of the game are that.
So if we want to decrease q, we can just decrease it. If we decide.
Yeah, but if you look for the solution, but now the rules of the game are again, I don't tell you what is lambda. I tell you what is Q, what are lambda i's, what is epsilon, what is delta. And you need to find all the alpha i's. How do you do that? You guess some value for lambda, okay? And then this equation tells you what are the alpha i's. Then you need to check what is the total output unit, and it will probably not be what you want. So you need to then tune this large lambda until you will get the correct output variance.
The estimated q or
So
q guess.
And what I'm saying is there is a one-to-one mapping between large lambda and Q. As you increase lambda, you decrease Q, and you need to implicitly find what is the correct lambda that will give you the correct Q. But I'm just saying this dependence is a decreasing monotonic dependence. As you increase, I could have phrased it in the opposite. To increase Q, we need to reduce large lambda. Okay? And so let me just write down the last element in what I've told you is that that what you actually do is that whenever large lambda is larger than lambda I star, we simply set alpha I to 0. So I want to summarize the solution. I'll do it here. I have no choice. So alpha I is given by alpha I of large lambda, lambda I, epsilon, and delta, if lambda is smaller than lambda I divided by delta lambda I plus epsilon, which is what we call lambda I star, and it's equal to 0 if lambda is larger or equal to lambda I star. That's the structure of the solution. And we have a constraint. Again, what we define, what I tell you in a given set of parameters is not large lambda and these parameters, it's Q. So we need to find what is the correct lambda to use. And this is set by the constraint that sum over I, alpha I, lambda I plus epsilon, minus is equal to m times large Q, which is also equal to m times Q minus delta. So now you know everything. Yes.
There is something like something special about this because the alpha is determined by the lambda that you find, and if this is the correct lambda or not, determined by alpha.
This is always the case when you have some equations, implicit equations that you need to solve. It's true. If I tell you what is lambda, you know what are the alpha i's, right? And then you can check what is this sum, right? And it will typically not be what you want. So now you tune, as you vary lambda, you will get something that changes here, and you will vary lambda until you get what you want. And that's the correct lambda to use.
Is there some update rule for lambda, or?
Well, since you will do an exercise at home of this style, what you will need to do is to solve, this is like solving numerically a nonlinear equation. And there is many ways to do it. MATLAB implements some of them, and you can just call a function in MATLAB that finds the root. Since this is numerically this is an easy problem because it's one-dimensional. You have just one parameter. So in principle, you could have plotted lambda Q versus lambda, or this sum versus lambda, and choose and find the position where it crosses, where you get the correct value. But you can do it numerically. Okay. Yes.
So even for the Gaussian case, we don't have an analytic solution.
Well, it's almost as analytic. It's as analytic as you can hope. You have an expression for everything. You just need to solve one nonlinear equation in order to find the correct parameter. It's very analytic still.
So it's okay.
We're very happy.
Okay.
Yes. Now, so I want to discuss some general lessons from what we've done, and then we'll start to apply this theory to an actual neural system, the retina. Maybe, so let's see. I'll write it here. So we discussed a projection from n inputs to m outputs. And I want to just mention some general lessons from what we've done. So the first thing is that by definition, when we do something like this, we reduce the dimensionality of the inputs. And what the theory tells us is that this is done in a particular way. This is done by projection to the first m principal component.
assumptions.
Of course, these are the generalizations coming under our assumptions, of course. Now, but this is a prediction. This is a very specific prediction that if a sensory system follows these rules and is adjusted to extract the first M principal components, then our brain should be completely insensitive to inputs that are outside of this subspace. So if we provide an input which is one of the other principal components, higher principal components, if the sensory system works like this, we should be completely insensitive to it. Okay? And now, the other very interesting lesson that we got, and I want to focus this when we discuss the retina, is that when we increase the input noise, we can get opposing. The behavior of how much resources our system allocates to these M components changes in a very qualitative manner. So as we increase the input noise, resources are shifted toward two components with large variance. So to the extent that we have completely different behaviors at very low and very high input noise, we saw that when the input noise is very low, we devote more resources to the components with low variance. The alpha I is monotonically increasing from components with large variance to components with small variance. And when the input noise is high, the opposite happens. We devote most of our resources to the components with large variance. And in fact, as we've just seen, when the input noise is sufficiently large, we completely discard some of the components with the low variance. This is also a prediction. We'll discuss that in the context of the retina. And I want to mention one thing which is a bit subtle, and this is that I would say that these two predictions are quite general, but these equations, or the equations that are written here, depend on an assumption which is less general, and this is what is the constraint. So our constraint was over the sum of the squares of the mean of the sum of the squares of the output units, and it's not, I discussed this when we started, it's not obvious that that's a correct constraint for a biological system. And if we would choose other forms of constraints, we might get some different equations for the alphas. These conclusions will still hold, but the details of these results might change. So constraints on the shared variance affect the details. We didn't try other constraints, but I am telling you that's the case. And so let me just mention this theory provides very strong predictions, but it also has some weaknesses.
Can I ask something about the alpha?
Yeah.
You still get qualitatively similar results even if you choose different constraints?
Yeah, reasonable constraints that constraint the total, activity of the output units. But the constraints could have been not the L2 norm, it could have been something a bit different. So I want to mention some weaknesses of the theory. One very significant weakness is that the theory actually doesn't tell us what are the receptive fields. Why doesn't it tell us what are the receptive fields? No.
Because we have the freedom
Yeah,
rotating.
because of the unitary transformation. So many possible forms for the receptive fields. Okay. W transpose can go to U W transpose. So, not clear whether the theory can, I mean, it tells us something about the receptive fields. They have to fall within this family of possible matrices, WPC, multiplied by some unitary matrix. But there are many, many different possibilities. And I would say that another weakness of the theory is just what I mentioned here, that the detailed predictions for alpha I depend on constraints. We could have chosen some. We have a constraint over this, but we could have had some constraint over the sum, say, I don't know, just to give you some examples. The sum of these things, or maybe sum over the mean of absolute magnitude of yi, or maybe the sum over the log of yi squared. It's not clear why we're choosing this one. Well, it is clear why we're choosing this one. We're choosing this one because this one is the easiest to treat mathematically. Okay, so what I want to do next is discuss a little bit the retina. And since I need to shift to slides, it's a good time to take a break. But let's not take a break which is too long. I had to start a bit late because I forgot my tablet. So maybe even if it's okay to take let's just take a 15-minute break. So we'll start a bit before 12.
למה יש פה
מה
מה
השורש?
המשמעות של פעמיים מלך
שמה?
פעמיים מלך מוחלט?
איפה פעמיים מלך מוחלט?
אחד מהאילוצים שם. אולי זה רק...
לא, זה סתם שטות. תודה.
ריבוע.
כן, זה פותר לך את זה? כאילו...
מה?
יש אי שוויון כזה של...
איפה?
כן.
ריבוע הוא כפול?
כן.
אוי,
זה לא האילוץ של הימני או האילוץ של...
זה מה שאנחנו עושים.
לא, אבל יש לו כבר באילוץ.
לא, כאן זה עם שורש.
לא, בהכי ימני.
זה עם לא אבל.
זה עם לא.
לא, זה אם לא. ומה המשמעות של הריבוע והשורש? זה לא נותן לך...
זה אומר שהאופן שבו אנחנו, אם זה היה output יוניט אחד זה לא היה משנה. אבל ברגע שיש כמה זה כאילו אומר איך אנחנו משקללים ביחד אותם, זה לא אותו דבר.
כאילו אפשר...
כי אין פרדיקציה לגבי איך המשקול אותם, כאילו איך...
זה שאלה קטנה, יכול להיות סתם...
רוצים שיהיה פרדיקציה, לא יודע, כאילו זה...
היה את המעניין השבועון של המטריצס, וזה אף פעם. ואז אמרת decrease Q, וזה גם קשר בין השניים. כאילו זה משהו כללי,
לא, האמת היא שלא הייתי צריך לעשות חץ כזה, כי זה טענה נוספת, זה פשוט מסתכלים על להסתכל על הביטוי שלך.
כן, זה כללי.
כן,
פשוט לא ראיתי את הקשר.
כן, אתה צודק.
איך הנוירון העניין שלוקחים עוד ועוד קומפוננטות זה דומה קצת, אני מניח שזה בא מסוג של אותו מקום ב-information bottleneck של טלי נגיד, אז יש שם את הפרמטר בטא הזה, אתה מכיר את זה?
אני מכיר, לא ברמה שאני זוכר איך הוא קורא לכל...
לא, אבל זה גם, זה מין כאילו, זה נהיה סוג של דומה ל-CCA באיזשהו שלב, נכון?
לא יש קונסטרנט על כל הקונסטרנט הוא קונסטרנט של אינפורמציה.
אבל פה בגלל שהכל גאוסיאני, אז קונסטרנט על הווריאנט זה כמו קונסטרנט,
אני מסכים.
כי בגאושן באטלנק אז הפתרון הוא גם, הוא מין CCA כזה, ואז ככל שאתה מרשה יותר וריאנס בקידוד, אתה משתלם לך לקחת יותר ויותר וזה, ויש מין פייס טרנזישן, כי כאילו עד שלב מסוים אתה נשאר...
אז נכון, מצוין, אז גם פה יש פייס טרנזישן.
אז זהו, זה מה שבאתי לשאול.
זה בהחלט, זה פייס טרנזישן.
כי עד שלב מסוים שווה לך להישאר עם מימד אחד, ופתאום ברגע מסוים יש איזה משהו קריטי
בהחלט.
אז זה ממש
כאילו האלפא עצמו הוא רציף, אבל הנגזרת שלו למשל, לפי ה-Q היא לא רציפה. היא 0 בצד אחד,
ואז כשאתה מגיע לערך...
אתה יודע, אולי הנגזרת, שאלה, אם הנגזרת היא... בטוח שנגזרת מסדר מספיק גבוה לא רציפה, אבל אם הנגזרת הראשונה כבר לא רציפה, איך אלפא מתנהג שם, השאלה אם הוא הולך ככה או אני חושב שזה כן, שהנגזרת לא רציפה.
אז יש כאן את העניין הזה.
אני חושב שכן, שזה דומה וקשור.
כן.
אוקיי, אם זה איזה הבטחה, כאילו, מהסמסטר, כאילו לא, כן, כאילו, הפרויקט הוא כאילו, כן, כן, כאילו, או להכין קוד של פייתון,
זה לא פאק.
עוד ככה זה אדיר.
מה זאת אומרת?
אני פעם הייתי לך שם. לא, זה אחלה.
Alright, so microphone.
All right, so before we talk about the visual system, I want to mention that the principles of what we've done apply to how multidimensional signals are encoded in digital systems. So if you ask yourself how is a picture, an image encoded by JPEG, or how is a movie encoded by the MPEG standard, it uses very similar principles. So for example, in JPEG, the image is divided into blocks of 8 by 8 or 16 by 16 pixels, and then all the encoding is done on these blocks. But within these blocks, the first thing which is done is that this block of values of pixels is linearly transformed to generate a based on the principal components of